Elixir Guides, Distributed Tasks and Configuration. In this chapter, we will go back to the KV application and add a routing layer that will allow us to distribute requests between nodes based on the bucket name. The routing layer will receive a routing table of the following format. So we have a list of a couple tuples, some pattern, and then route to this pattern name. The router will check the first byte of the bucket name against the table and dispatch to the appropriate node based on that. For example, a bucket starting with the letter A, $A represents the Unicode code point of letter A, will be dispatched to node foo at computer name. If the matching entry points to the node evaluating the request, then we've finished routing, and this node will perform the requested operation. If the matching entry points to a different node, we'll pass the request to this node, which will look at its own routing table, which may be different from the one in the first node, and act accordingly. If no entry matches, an error will be raised. You may wonder why we don't tell the node we found in our routing table to perform the requested operation directly, but instead pass the routing request onto that node process. While a routing table as simple as the one above might reasonably be shared between all nodes, passing on the routing request in this way makes it much simpler to break the routing table into smaller pieces as our application grows. Perhaps at some point, foo at computer name will only be responsible for routing bucket requests, and the buckets it handles will be dispatched to different nodes. In this way, bar at computer name does not need to know anything about this change. Note: we will be using two nodes in the same machine throughout this chapter. You are free to use two or more different machines on the same network, but you need to do some prep work. First of all, you need to ensure all machines have a .erlang.cookie file with exactly the same value. Second, you need to guarantee EPMD is running on a port that is not blocked. You can run EPMD -D for debug info. Third, if you want to learn more about distribution in general, we recommend this great Distribunicon chapter from Learn Use Some Erlang. Our first distributed code. Erlang ships with the facilities to connect nodes and exchange information between them. In fact, we use the same concepts of processes, message passing, and receiving messages when working in a distributed environment because Elixir processes are location transparent. This means that when sending a message, it doesn't matter if the recipient process is on the same node or on another node. The VM will be able to deliver the message in both cases. In order to run distributed code, we need to start the VM with a name. The name can be short when in the same network, or long, requires the full computer address. Let's start a new IEX session. So IEX -sname foo. You can see now that the prompt is slightly different and shows the node name followed by the computer name. My computer is named JV, so I see foo at JV in the example above, but you will get a different result. We will use foo at computer name in the following examples, and you should update them accordingly when trying out the code. Let's define a module named hello in this shell. So def module hello to def world puts hello world. If you have another computer on the same network with both Erlang and Elixir installed, you can start another shell on it. If you don't, you can start another IEX session in another terminal. In either case, give it the short name of bar. Note that inside this new IEX session, we cannot access hello.world. However, we can spawn a new process on foo@computername from bar@computername. Let's give it a try. Node spawn link, then we give it foo@computername and a function to run, so hello.world. Elixir spawned a process on another node and returned its PID. The code then executed on the other node where the hello world 0 function exists and invoked that function. Note that the result of hello world was printed on the current node bar and not on foo. In other words, the message to be printed was sent back from foo to bar. This happens because the process spawned on the other node, foo, still has the group leader of the current node, bar. We briefly talked about group leaders in the I/O chapter. We can send and receive messages from the PID returned from node.spawnlink2 as usual. Let's try a quick ping pong example. So PID, node spawnlink, foo, and then on receive ping client, send client pong, send ping self flush. From our quick exploration, we could conclude that we should use node spawnlink 2 to spawn processes on a remote node every time we need to do a distributed computation. However, we have learned throughout this guide that spawning processes outside of supervision trees should be avoided if possible, so we need to look for other options. There are 3 better alternatives to node spawnlink 2 that we could use in our implementation. We could use Erlang's RPC module to execute functions on a remote node. Inside the bar@computername shell above, you can call rpc.call foo@computername, then hello world and args, and it will print hello world. Another option is we could have a server running on the other node and send requests to that node via the GenServer API. For example, you can call a server on the remote node by using genserver.call name node arg, or passing the remote process PID as the first argument. Finally, we could use tasks, which we have learned about in a previous chapter, as they can be spawned on both local and remote nodes. The options above have different properties. Both RPC and using a gen server would serialize your requests on a single server, while tasks are effectively running asynchronous on the remote node, with the only serialization point being the spawning done by the supervisor. For our routing layer, we are going to use tasks, but feel free to explore the other alternatives too. Async await. So far, we have explored tasks that are running in isolation, with no regard for the return value. However, sometimes it's useful to run a task to compute a value and read its result later on. For this, tasks also provide the async await pattern. So task equals task async, and then the function compute something expensive, then result compute something else, and then result plus task await the task. Async await provides a very simple mechanism to compute values concurrently. Not only that, async await can also be used with the same task supervisor we have used in previous chapters. We just need to call task supervisor async 2 instead of task supervisor startchild 2, and use task await 2 to read the result later on. Distributed tasks. Distributed tasks are exactly the same as supervised tasks. The only difference is that we pass the node name when spawning the task on the supervisor. Open up libkvsupervisor.ex from the kv application. Let's add a task supervisor as the last child of the tree. Task supervisor name kv router tasks. Now, let's start two named nodes again, but inside the kv application. From inside bar at computer name, we can now spawn a task directly on the other node via the supervisor. So task supervisor async, kv route tasks, foo at computer name, and then the function, and then await that task. Our first distributed task receives the name of the node that the task is running on. Notice we have given an anonymous function to task supervisor async2, but in distributed cases, it is preferable to give the module, function, and arguments explicitly. Notice that the difference is that anonymous functions require the target node to have exactly the same code version as the caller. Using module, function, and arguments is more robust because you only need to find a function with a matching arity in the given module. With this knowledge in hand, let's finally write the routing code. Routing layer. Create a file at libkvrouter.ex with the following contents. So we have this route function, dispatch the given mod, fun, and args request to the appropriate node based on the bucket. Let's write a test to verify our router works. Create a file named test.kvroutertest.exs containing the first test invokes kernel.node0, which returns the name of the current node based on the bucket names hello and world. According to our routing table so far, we should get foo at computer name and bar at computer name as responses, respectively. The second test checks that the code races for unknown entries. In order to run the first test, we need to have two nodes running. Move into apps kv and let's restart the node named bar, which is going to be used by tests. So ix sname bar, capital S mix, and now run tests with elixir sname foo smix test. The test should pass. Test filters and tags. Although our tests pass, our testing structure is getting more complex. In particular, running tests with only mix test causes failures in our suite, since our test requires a connection to another node. Luckily, XUnit ships with a facility to tag tests, allowing us to run specific callbacks or even filter tests altogether based on those tags. We have already used the capture log tag in the previous chapter, which has its semantics specified by XUnit itself. This time, let's add a distributed tag to test.kvroutertest.exs. So tag distributed. Writing tag distributed is equivalent to writing tag distributed true. With the test properly tagged, we can now check if the node is alive on the network, and if not, we can exclude all distributed tests. Open up test.helper.exs inside the KV application and add the following. Exclude equals if node alive, do this, else distributed true. And then xunit start, exclude, exclude. Now run the tests with mix test, and they're excluded. This time, all tests passed, and xunit warned us that distributed tests were being excluded. If you run tests with Elixir sname foo S mix test, one extra test should run and successfully pass as long as the bar at computer name node is available. The mix test command also allows us to dynamically include and exclude tags. For example, we can run mix test include distributed to run distributed tests regardless of the value set in test.helper.exs. We could also pass the exclude flag to exclude a particular tag from the command line. Finally, only flag can be used to run only tests with a particular tag. So, only distributed. Application environment and configuration. So far, we have hard-coded the routing table into the KV router module. However, we would like to make the table dynamic. This allows us not only to configure development, test, production, but also to allow different nodes to run with different entries in the routing table. There is a feature of OTP that does exactly that, the application environment. Each application has an environment that stores the application's specific configuration by key. For example, we could store the routing table in the KV application environment, giving it a default value and allowing other applications to change the table as needed. Open up apps kv mix.exs and change the application function to return the following. So now we have env routing table. We have added a new env key to the application. It returns the application default environment, which has an entry of key routing table and a value of an empty list. It makes sense for the application environment to ship with an empty table, as the specific routing table depends on the testing deployment structure. In order to use the application environment in our code, we need to replace KV router table with the definition below. So now instead of explicitly setting it to a routing table, we do application.fetchEnv and then KV, which is our application, and then the key within that routing table. We use application fetchEnv2 to read the entry for routing table in KV's environment. Since our routing table is now empty, our distributed tests should fail. Restart the apps and rerun the tests to see the failure. The interesting thing about the application environment is that it can be configured not only for the current application, but for all applications. Such configuration is done by the config.exs file. For example, we can configure IEX default prompt to another value. Just open up apps kv config.exs and add the following to the end. So config IEX default prompt, triple pointy bracket, and then start IEX, and you can see the IEX prompt has changed. This means we can also configure our routing table directly in apps kv config.exs file. So now we have config kv routing table, and then the route tuples that we had from above. Restart the nodes and run distributed tests again, and now they should all pass. Since Elixir 1.2, all Umbrella applications share their configurations. Thanks to this line in config.exs in the Umbrella root that loads the configuration of all children. Import config apps star config.exs. The mix run command also accepts a --config flag, which allows the configuration files to be given on demand. This could be used to start different nodes, each with its own specific configuration. For example, different routing tables. Overall, the built-in ability to configure applications and the fact that we have built our software as an umbrella application gives us plenty of options when deploying the software. We can deploy the umbrella application to a node that will work as both TCP server and key value store. Could deploy the KV server application to work only as a TCP server as long as the routing table points only to other nodes. Or we could deploy only the KV application while we want a node to work only as storage, no TCP access. As we add more applications in the future, we can continue controlling our deploy with the same level of granularity, cherry-picking which applications with which configuration are going to production. You can also consider building multiple releases with a tool like Distillery, which will package the chosen applications and configuration, including the current Erlang and Elixir installations, so we can deploy the application even if the runtime is not pre-installed on the target system. Finally, we have learned some new things in this chapter, and they could be applied to the KV server application as well. We're going to leave the next steps as an exercise. Change the KV server application to read the port from its application environment instead of using the hardcode value of 4040, and change and configure the KV server application to use the routing functionality instead of dispatching directly to the local KV registry. For KV server tests, you can make the routing table point to the current node itself. Summing up. In this chapter, we have built a simple router as a way to explore the distributed features of Elixir and the Erlang VM, and learned how to configure its routing table. This is the last chapter in our Mix and OTP guide. Throughout the guide, we have built a very simple distributed key value store as an opportunity to explore many constructs like generic servers, supervisors, tasks, agents, applications, and more. Not only that, we have written tests for the whole application, got familiar with XUnit, and learned how to use the Mix build tool to accomplish a wide range of tasks. If you are looking for a distributed key value store to use in production, you should definitely look at Ryak, which also runs in the Erlang VM. In Ryak, the buckets are replicated to avoid data loss, and instead of a router, they use consistent hashing to map a bucket to a node. A consistent hashing algorithm helps reduce the amounts of data that needs to be migrated when new nodes to store buckets are added to your infrastructure. Happy coding. All right, I'm going to be right back with maybe some metaprogramming. Maybe, what do we got here? Yeah, I could do this. I'm going to just walk around for a second.